So historically, where do these things come from? They actually come from different roots, completely different roots. They kind of procedures and functions are sort of seen as the same thing in programming, but they actually are completely different in terms of where they came from, what they really mean. So historically, in computer engineering and computer programming, in the early days of programming, the idea of procedures or subroutines, right? This idea of subroutines comes from the fact that you wanted to do something in your program very often during the execution of the program, and so there was obviously, instead of repeating, copy pasting the same thing sequentially, right? You would put this thing in one place of your program, and then you would have these long jumps that you jump to the beginning of that block whenever you want to run it, and then you would jump back whenever you were done running that thing. So that sort of, it came from people realizing that there are certain subparts of the program that needed to run multiple times. So that's sort of, in terms of the engineering side of things, it comes from necessity of doing that act without copy pasting the same code over and over and over again. It was probably one of the first constructs in programming after people realized that they could have the program sequentially, right? So the first construct was, oh, wait a minute, there's a lot of code here that is repeated. Why don't we invent something that we just put this in one place, and then we have some sort of an instruction to jump there, and then an instruction to jump back to where we were. So subroutines are sort of the origins of procedures. They may have no arguments at all. You just jump there without any arguments, just do something there. You can send it arguments, one or more. They can return things or not. At the end they can return something, or they can return nothing. It doesn't matter. It's just, the idea was that was really some procedure that you wanted to do multiple times, and the issue, the arguments and return values was secondary. And it can perform, can do whatever it needs to be done. All the actions, I/O, side effects, change the memory, change everything. So this is sort of in the mid-50s. Functions, however, functions are interesting because functions come from mathematics. The roots of functions is just mathematics. It's mathematical functions. So what are functions? Functions are relations that take some input and produce some output. That's the definition of a function, right? And the constraint with respect to all the relations is that the same input always has to map to the one output. So you cannot have one input that maps to two outputs. It has to be deterministic, right? That's the definition of the function, that you give it one input and the output is always the same for that particular input. But so that's the definition of a function in mathematics. They take input arguments, they return one value, and they are used as what's called expressions. So additionally for pure functions in the programming world, because there's a fine line between functions and procedures, the idea for pure functions is that there are no side effects. So functions are supposed to be just mathematical functions. So they're not supposed to write on the screen or send packets over the network or do whatever. They are not supposed to change the state of the world, okay? That's the definition. The definition of a function, a pure function, is a function that just takes an input, returns an output, and it's gone. And nothing remains of its execution. No side effects. So the distinction between procedures and functions kind of actually existed in the beginning. That's the interesting thing. It existed in the beginning of programming. It was in 1958 Fortran already had the distinction. So here's an example of Fortran. This is a subroutine, so a procedure. So you define a subroutine square cube. and it takes an input, it returns some output. Right, so this is a subroutine that returns both the square and the cube of a given input. Okay, so it does two things at the same time. So you give it an I and it returns both the square and the cube. So it has two output arguments. And so when you call this subroutine, that's how you do it in Fortran 58. So you got down there on the red statement, call square cube. So this was a subroutine in Fortran 1958, and this was a function. So Fortran had a distinction, a syntactic distinction. So the keyword subroutine was different than the keyword function. And a function is exactly what I said. It takes an input and returns an output. That's it. So in this case, it just it returns the sum of the square and the cube in this particular case. And it's not called, as you can see down here in the program, it is not called as a subroutine. It's just invoked. So you say print, that is the print statement over here, and then you just invoke it, func of I, all right? That's it. And additionally, Fortran has a pure keyword for pure functions that were not supposed to even print anything, right? And so this one is actually a pure function too. But you could denote it to be pure, that there was some enforcement on the compiler that it didn't have no side effects. So this was quite interesting. In 1958, Fortran had this distinction between what was supposed to be just a mathematical function that was used almost sort of as a built-in or not a built-in, an inline kind of thing, something that you could just replace, just a syntactic replacement. And then a procedure that was something a lot more complicated and could have side effects and all that stuff. But somewhere along the way, that distinction was lost. And the mainstream programming languages kind of merged these two concepts into one. And you see, I bet that none of you has ever thought that there was ever any difference between a function and a procedure, because you have been using these words kind of interchangeably, I bet. Because that's what all of these languages do. So, you know, in C, C++, Java, Python, Perl, there's no distinction. So procedures can return values, procedures can be functions, functions can have side effects. So it's just, there's basically just one thing. There's no two things. There's just one thing. There are functions that act as subroutines, or vice versa. Subroutines that act as functions. In the functional languages, there are only functions, especially the like ML and Haskell, the more pure functions are only functions. But the functions can be pure or impure. So you can tag some functions saying, okay, so this function can have side effects, or this function cannot have side effects. And that's where you make a distinction between a true function that's pure and something that's more procedure-like, which can have side effects. So what is pure functional programming? Basically, the idea, pure functional programming is an interesting thing. It's something that comes from mathematical functions. So what are functions in mathematics? If you look back into mathematics, where you studied functions, that's it. You know, that's a domain and the counter domain and a domain and the range, right? And then you pass it an input and you get an output out of the range, and that's it. There's no changing the world. Nothing changes. When you calculate the value of a function, nothing in the world changes. If you just get that result, that's it. Now, there's no I/O, nothing, you know, maybe in the beginning there's I/O, in the beginning that you get the input, and then at the end you get the output from the function. You can consider that to be I/O, but there's no I/O in terms of like, you know, changing the world, okay? But another thing that also happens in mathematics, and particularly when you go to first order logic and things like that, that functions, the arguments to functions can also be functions. right? So you can have functions that can take just normal numbers as inputs and outputs, but you can also have functions that take other functions as inputs and outputs. Those are called higher order functions, right? So, and those are, I'll talk more about these. They're super powerful in terms of what they represent in programming, even if you never heard of them before, but you've used them at least. So let me just go through some slides that explain sort of very basics of how to implement these concepts. And I'm just calling it these concepts of function or procedure that has all been kind of mushed together in mainstream programming languages. Because at the bottom, in almost all of the language processors, they're almost all implemented in the same way, okay? And I alluded to this in the last lecture, the fact that, this is a simplified machine model, and there is this stack, right? The stack is used for keeping track of where you are in a chain of calls to functions, right? Because then you need to be able to return to where you were. You need to be able to do recursive calls, right? You have to be able to call a function many times in a sequence of function calls without returning from the first one, right? And that can only be done if you have some sort of a management about where you are, and that's done by the stack. So let me talk a little bit. So there's a prototypical example of a recursive call, factorial, that takes a factorial of n, and if n is less or equal than 1, then it returns 1. Otherwise, it returns n times the factorial of n minus 1. So this is the prototypical recursive function. And I'm going to use it because recursion is one of the reasons why stacks were brought in for language processing in general. Because if we did not allow recursion, right? If we had a programming model that you didn't allow recursion, for example, you could call a function, but you could, for example, you could not call the same function without exiting it first. Okay, if you have that constraint, then you don't necessarily need a stack to keep track of things of where you are. Because you can just lay the functions basically in memory and they're just there, right? So you just put them in memory and now you just call them, you kind of jump from one to the other, and you don't need to necessarily have this stack thing. But when you start having recursive calls, okay, and basically you have the same activation, you have multiple activations of the same function, then you really need to have some sort of an order, which one was activated first, right? Otherwise, you don't know. So a stack maps very well to that kind of a situation. So if you call it here factorial of 3, what's going to happen? And this, by the way, what I'm going to explain happens now on any chain of function calls. It doesn't need to be recursive, okay? I'm just going to use the recursion example because it's the most striking example that you really need a stack, but the stack is used for even if it's not recursive, okay? So there's this concept of an activation record for functions, which is a data structure that describes the context in which the function is being called. What are its arguments? Where do you return back? Leave a space for the return value if it has a return value, leave a space for the parameters, the local variables, right? Everything that has to do with that particular activation of that function. You need a place in memory to hold it. So that's sort of what's called the activation record, or also known as stack frame. Okay, so those are the two different names. So it typically has this kind of information. So the parameters, the local variables, the return address, the location to put the return value when the function exits, controlling to the call of the activation record, save registers, temporary variables, intermediate results, and maybe an access link to the function's static parent, but not always. So something like this. All right, and in particular, the return address is important, so the location of the code to execute on the function return. Oh, all right. So here's an example. Okay, so here's a factorial definition. The return result address is the location to put the value that gets returned from calling factorial of n, right? Some value gets returned from that call, and you need to put it somewhere. The parameter set to value of n by calling sequence. So that you need to have a place to put the n, the actual value of the n that you call. So here's more examples, in particular a typical x86 activation record. I call on the stack. All right, so let me just go. I think I have a series. So there you go. So if you have a factorial of 3, cofactorial of 3, right? So you the n, here's the place to store the argument, okay, that you send it. So n is 3. This is the number n binds to 3. The result of calling this function is going to be placed here somewhere, right? So that's the result of calling the next function, because you're going to call the next function, right? Call the next function, and then there's a new activation record, okay? This activation record is n equals 2, because we call it with n minus 1. And then you need to leave space for the return of you called n minus 1, right? When you call n minus 1. And so, etc. So, and as you can see, there's these pointers on the next frame that point to where to put the result, right? Where to put the result. Okay. So finally, when you get to factorial of n minus factorial of 1, then you don't call the factorial function anymore. You just return 1, and then you basically pop all this stuff, all of these activation records, and you put the right values in these spaces that you left to put the values, the returned values, right? And then that's where you get the final value. So this is how it's managed, how these things are managed. So here you go. You first build the recursive chain, right? And then you place the 1 there. That was the return of factorial of 1. And then you pop again, maybe, no, I don't have it here, the animation. But then you pop again, and then you place the return value, which is 2, factorial of 2. And then you pop again, okay? Finally pop and get the result. So this is how functions / procedures are handled in almost all of language processors these days. So takeaway about functions. Functions are ephemeral. They execute and go away. The pure functions are the most ephemeral of all. So they don't even leave any trace that they existed. They're actually very good for concurrency, for testing, for all sorts of interesting things. Now I don't have more slides, but I'm going to talk about what does this mean for the basics of programming. Okay, so let me go to the exercises and go through the examples on part 2 of the book. So the most basic examples. So style number 4 is the monolithic style. So the monolithic style, I'm going to so the monolithic style is characterized by the absence of abstractions, by the absence of dividing the problem into smaller problems. There's no such thing. You have a problem, and the way that you solve it in monolithic style is that you solve it starting line 1, and then you basically try to do everything. I try to do everything with the control flow, loops and iterations and stuff like that, and conditionals and all that stuff. So this is a style that comes very naturally to a lot of C programmers. Let me show you how to solve the term frequency program in this monolithic style. You basically this is where you're going to put the word frequencies map. You load up the stop words, and then here's a big monolith, right? So you have a ginormous loop for every line, right? So you open the file and you iterate through every line, and then for every line you iterate through each character, right? And then there's logic now, complicated logic that rules whether this is the beginning, of a character of the line, whether you've seen an empty space or not, whether you've seen an alphanumeric a letter or not. Basically, it's a complicated logic that works, but it's complicated. It's hard to understand what is going on. So it's basically two nested loops, and then conditionals. Here's one conditional, more nested conditionals, and it's doing everything. Basically, as it traverses through each character, right, of the line, it's doing the higher level logic of identifying words, of counting the words. So it's doing everything at the same time. So basically, this is a situation where there are no procedures, right? There's no functions, no procedures. It's just this one thing, brain dump, right? The dump. This is sort of a quick and dirty way of thinking about temp frequency. And I don't, sometimes the monolithic style is justified, okay? There are some times that it's justified, but it makes the code very hard to read, that's for sure. I bet that I don't even remember very well what was the logic that I put in here, but I know that it's kind of hard to read, as you can see. Any comments about this style? So one thing that is clear in here is that there are things in here, for example, see if the word, for example, ignore the stop words, okay? So ignoring the stop words is something that perhaps we could think, okay, maybe this is some abstraction that we want to have, some abstraction in here that we're going to check if it's a stop word or not, okay? And in here, it's completely diluted. It's part of the logic. It's sort of, you don't even notice that there's something important going on in here, right? Same thing for whether to, when you put the word or when you identify the words, like for example, when you identify the word, where is it? We found the end of a word, right? Okay. Right. So this is just really, really hard. We found the word. That's an important thing, right? We found the word, and then we should be doing something with that word. More higher level, at the word kind of level processing, rather than mix it up with character level processing, right? So this monolithic is mixing different scales. It's mixing the characters with the words, and clearly, once we have a word, there's further processing that what we're doing with the word that calls for a little bit of a higher level of abstraction than what is in here. And that this is the opposite of that, right? So this is the absence of procedures and functions. It's just a like sequential brain dump of trying to do everything at the same time. Very hard to read this program. So now let me go into another one, which is the cookbook. So the cookbook this one really tries to do the right thing. So this one tries to divide the problem into smaller problems, and this is how we all learn how to program. Maybe, I hope, maybe, I don't know. But this follows the idea that when you have a big problem, the idea is that you divide it into smaller things. Okay? You just divide it to smaller things, and then you code up a function for each one of those smaller things, and then or whatever, you can call up something, so some form of abstraction, and then you invoke those abstractions at in the right time. So in this particular case, we divide the bigger problem of term frequency into these abstractions. So for example, reading a file. Okay, read the file is one abstraction here, and we just read the file. We load up the file into memory. Okay, and whenever if we need it to do this many times, it's already this procedure here is already here. Another thing that we need to do is to filter the characters and normalize them, right? So ignore everything that's not alphanumeric, put everything to lowercase. So character processing, right? Character processing is also an abstraction in here. So it's this little abstraction over here. Filter characters and normalize. Another thing is once it's normalized, then we want to identify the words. So that's scanning for the words. So it's another part of the problem, and so we define a little procedure in here that given the sequence of characters, we find the words. We split it into words. So here's the little abstraction that does that. And then once we have a list of words, then the next thing that we need to do is to remove the stop words. So we remove, here's an abstraction to removing stop words from a list of words, all right? And finally, once we cleaned up everything, we take out the words that we don't want, then we count, okay? So then here's an abstraction that counts things, all right? It traverses the list of words and it counts them, all right? Puts them in these word frequencies data structure. And finally, once we have those counts for all the words, then we sort them, okay? Then we sort the words and by count, and then we print it out. Okay, and the main function, this is the part that we define all these procedures, and the main function is just a cookbook. So you first read the file, and then you filter the characters and normalize, and then scan. You could tell this in kind of cookbook stuff, right? This is a recipe. Scan, break the egg, mix the egg with the sugar, then beat for 5 minutes, and then add the flour. So that's basically what this is about. And as we are doing this recipe, we are changing the state of the world. That is the important thing. One thing that this style does is that it recognizes the need to divide a big problem into smaller problems. That is good. Okay, this is a good thing. But the other important thing, the way that it does it, it's that it assumes that we are doing a cake, right? That we have some sort of, matter, here's this state over here, the shared mutable data. And this is the things that we read and mutate and change and update and assign as we are doing our recipe. Really like we are doing a cake. We're transforming, we're updating, we're changing the state of the world by calling these procedures, right? So this is an important characteristic of the cookbook style. It's sort of very Pascal-like, that you have some sort of a global or pseudo-global or something that is shared among a bunch of procedures, some state that is shared among a bunch of procedures, and all of those procedures can change that state. Okay, they operate on that state, that shared state, and they can all read them and write them. Okay, it changes as the procedures execute. Right, so that is a characteristic of the procedural style of programming. So now let me move here to another one, so style number 6. So number 6 is the pipeline, and the pipeline is, interestingly, almost the same as the cookbook. It's almost indistinguishable from the cookbook, but there's something that is really subtle but super important. So here's the thing, the division of the problem into smaller problems is there, and it's actually exactly the same. Right? So here I can call them functions. They are exactly the same. The read file, filter characters, normalize, scan scan for the words, remove the stop words, because they're exactly the same. Now, one important thing is that these now are functions. They're not just procedures. And what it means is that, oh man, hold on just a second. My dog's going crazy. Hold on just a second. All right. And I see that there's chat that I missed. Okay, what's the difference between intermediate result and local variables? Okay, sorry, Aditya, I didn't see that question. Okay. Intermediate results and local variables. I don't know. I don't remember very well. They're probably, no, I know. So sometimes there are some functions that you call somewhere, maybe in the middle of a loop or something like that, that doesn't necessarily have, it's not necessarily assigned to a local variable, but that you use to pass it to some other function, for example. So that's an example of an intermediate result. And another question from Aditya, when will you use this kind of style? Which style were you using, the monolithic one, Aditya?
Yes, the monolithic one.
Yeah, the monolithic one. So I've seen sometimes successful uses of monolithic style when the logic defies abstraction. I've seen some situations where you try to abstract the problem and it just doesn't feel right. And the thing that just feels right is just, whatever, do two loops, nested loops, and two conditional or whatever, nested conditionals, and that is somehow it's the best description of the situation. It doesn't happen very often. But sometimes I've seen situations that the best description of the situation really is that nested control flow, and it's the way that it feels the natural mapping of the problem. Because yeah.
So maybe sometimes like in matrix algorithms.
Yes.
Okay.
Okay. So I was talking about the pipeline style that is almost the same as the procedural one. But as you see, the global state is gone. There's no global state. Okay, there's no variables. There's no global state, and all of these abstractions now are actual functions. I mean, in the sense that they all take an input and they all return something at the end. Okay, so here it is. They all return something. They all take something, and they all return something. Okay, if you looked at the other one that I showed you, that was not true. They all worked over the shared variables, the global variables. And so if you look down here in the main function, this one looks completely different now, right? So this is not a sequence of recipe. It's not the sequence in a recipe. What you have now is the sort of the true mathematical function composition, which is print all, after sort, after frequencies, after remove stop words, after scan, after filter charge normalize, and after read file. So I don't know if you remember, the function composition in mathematics, you have, for example, G, and then you have that little circle that denotes after F. You all remember that mathematical notation of the function composition, which has the weird property, at least for me, weird, that you end up, I mean, maybe it comes from Arabic, I guess, because you end up writing from right to left, right? The first thing that happens here is reading the file, and it's on the right side. And then the second thing is the next one, and the third is the next one. So you're writing from right to left. And by means of using the function composition of mathematics. But basically, with respect to state, all right, so that's the important thing. With respect to state, what's going on in here is that there's no global state. There's no state, right? There's no state at all. You give an argument to the first function, and then that first function returns some value that is then chained to the next one, and that one returns some value that is also served as input to the next one, right? So there is no state. It's just a series of function calls chained together. Now, these are not pure functions. You should note. So many of them are not pure functions, in the sense that they change the state of the world. So what does that mean? For example, reading a file clearly has to interact with the file, so it's reading the file. Another one here, for example, frequencies, maybe, but for example, the print, okay, print all is definitely a stateful, it has side effects. It's actually printing things on the screen. That's a side effect. But let me zoom into little details. For example, scan. Okay, here's the scan function. The scan function takes a string and scans for words, returning a list of words. So it's actually quite pure. Okay, it doesn't destroy anything. It doesn't change anything. It takes a string and returns something else that it creates that is a list of words. It does not destroy the string. That's important. Nothing is destroyed. So that's important for functions. For example, the remove stop words, it takes a word list as input and returns another word list without removing anything from the input. That is an important thing, and that may be a strange thing for people who are, again, used to C programming, where memory is sort of a major concern. And you know, you have a function that receives a list of words, and you're supposed to eliminate certain words from that list. The tendency is to actually destroy the list, basically to just remove in that list that you get, you just reuse it and you just remove certain elements from that list, right? That is not what's happening here. What's happening here is that you are creating, this is the creation of another list that consists of words for which the word is not in the stop words. So there's a creation, there's extra memory being generated here. This is an important detail, that nothing is being destroyed from the original list. So this is pretty functional, pretty pure functional, and etc. So same thing here. Sorting. Okay, sorting is also. Let me see if that is true. I think sorted is also does not destroy the input that it gets. It also returns something else that it creates. And the reason I'm pointing this out is that I'm already pointing this out as one of the characteristics of pure functional programming is that nothing is destroyed. So if you get something, you read it and you leave it alone. You don't change it. If for example, if you get a list or whatever, a string, and you just need to change one tiny character on that string, you don't change that original string. You make a copy, and in the process of making a copy, then you change that one thing. You create something else. There's always sort of the idea of the pure functional programming that you don't update things. You always create copies of things. So this may be very, very strange for people whose main concern is optimization and memory. Oh, man. Let's turn this off. I should remember to turn off all of my cell phones. But that is definitely one of the characteristics of pure functional programming and pure functions, and what's called immutable data structures, and the idea that you try to change as little as possible for a number of reasons. All right, so you have a question here from G1. The file okay, so Glenn has said that it has I/O but isn't changing the file. Right, the file could be changed and the function will not be aware of whether it's changed or not. That's a really good discussion that is going on. So let's go here, look into the read file definition. I mentioned that this one is having side effects, so it has something. And Glenn mentioned that, well, maybe it's not having side effects because it doesn't change anything, right? So it's just reading the file but it's not changing it. And that is true. However, one of the problems, but it has I/O, it has input, it has like device input, right? So it reads the file. One of the problems with reading from the outside world or interacting with the outside world is that the outside world can be very unreliable. And in particular, for example, in here, you can give it a path to a file, and at one time, that path can be there and you read it successfully, and at another file, you just happen to have deleted that file, and this function is going to fail because now it doesn't find the file. Okay, so one thing that functions hate, okay, in mathematics is that for the same input that you have two different behaviors. That is not in the purview of mathematics. For the same input, you were always supposed to have the same results. That's what the function means. So if it can happen at any time that you give it the same input one time and you get a result, and you give it the same input another time and you get a different result, then that's not a function, okay, by definition of a function in mathematics. So that's why I'm pointing this one out as having as not being a pure function. It's because the rest of the world can change from under it, and it can have a different behavior. Okay, so all right. So one of the interesting consequences of functional programming, the reason why functional programming was kind of shunned for a long time, was because it appears that it is very inefficient. Okay, and this is what where I'm getting at is that if you really follow the principles of functional programming, that you don't ever destroy anything, and that you always create new things, right? And then memory use is super inefficient because you'd be always creating copies of things just to change a tiny little thing. And that has been sort of an argument throughout the 70s, where functional programming was already in use in Lisp, in the form of Lisp and ML even more. But you know, that was the golden days of procedural programming, like languages like C and Pascal. And you know, they were clearly faster. The programs are much faster than the programs written in the functional languages, obviously. And so the functional programming had sort of a bad reputation at the time for being slow and inefficient. And you know, people were like, why would you not want to optimize memory usage? And you know, and that was all fun and at the time until compilers in functional programming started getting really good, and they started doing those kinds of optimizations that people were doing by hand in C, right? So it turns out that a lot of these memory management optimizations that we do in C and C++, a lot of them can be automated, okay, with the right abstractions and the right expressions and the right compilers. A lot of those things can just be automated. So the model is that nothing is ever destroyed. That's the programming model. That's what the programmer sees. But underneath, it may not be like that at all, okay? Things may be destroyed, but that's just an optimization, and it doesn't transpire to the model or that you are programming with, and you don't see it. It doesn't affect what the program is how the program is going to behave. And that was, you know, those advances in functional programming really made a difference more recently, starting in the, you know, in the 2010 and things like that, or even in the early 2000s, things started to change, and people started paying a little bit more attention in functional programming. But clearly, the first encounter with something like this is like, wow, this is going to be super inefficient, right? So imagine that we're dealing with a very large file, and immediately the first function is already loading the file into memory as a whole. That's already a bad idea, because it may explode because the file may be too big, and not to mention the fact that then you're creating new things in all of these functions. They're creating new things rather than kind of transforming the data as you go along. So that was clearly sort of something that people had to get used to, coming from more imperative style and procedural style kinds of programming. And I will talk more about some of these optimizations as we talk about functional programming. So that is the pipeline style. Very, very basic, just the idea of function composition down here. Okay, function. There's no global variables, no variables at all. There's just functions with the take input and return output. That's it. And this program happens to, some functions are not pure, but it's still functional. And now let me talk about another one here in part 2, which is the code golf. It's part of your exercise too. So the code golf is an interesting style that you see in many places, and it's good advice, right? That if you can write something short, you should write it short. And if you can write something, one line of code, then instead of 10, then you probably should write it in one line of code instead of 10. And this comes to the question of length, of size, in program size, which is a kind of an interesting topic by itself. So here's the term frequency in Python written by Peter Norvig, which is a famous computer scientist who works at Google. I had a version of this. I had some version of this code golf on my repo, and then out of the blue, one day he sent me this version that was 1 or 2 lines short. And his email was exactly just this, nothing else, just including the comments and everything. It was quite funny. So anyway, so here's what this is doing. It's using it's using a very powerful, already existing instructions in the Python libraries, okay, to have a very short, concise program. So the first line loads up the stop words, okay, and it's already in a list. Okay? It creates a list of stop words, and it actually makes sure that there are no repeated stop words, because apparently in my file I have repeated stop words or something. The second line reads the input file, okay, transforms everything to lowercase, and then finds all the words, that means all the sequences of characters that have only letters, okay, here's the regular expression, A to Z, and that are at least 2 characters. That's what this regular expression means. Okay, so this is all sequences of letters that are at least 2 characters. Bang, find all, using the regular expression library, we have a list of words. Okay. All right, and the next line is counting, and it's using a very powerful collections library that Python already also has, and it has basically a counter that does the counting for us. So, and we give it a list of words that are not in the stop words, and it returns some sort of a dictionary of words and counts. And it also has a function for most common, so it actually sorts them too. So it does everything for us. And one interesting thing about this particular code golf is that it's actually very, very readable. In fact, for many of you, during the last week when you were asking me for or having questions about the specification of the problem, I pointed you to this solution because for me, this is one of the most readable programs in my collection. It's just it's so simple. You look at this and you see exactly what is going on, right? And it's super short, and you see the what, you don't necessarily see the how, because the how it's hidden in these libraries, right? It's in the regular expressions, the collections library, it's all in there. I don't know how it does it, but I know what it does. Okay, and so this is an interesting thing. You know, making the programs short, what is something that sort of a badge of honor among certain programmers, certain cultures in programming, and short, you know, conciseness in itself is not necessarily a good goal, okay? Because you can have programs that are very short and totally unreadable, okay? You just don't understand what they are, what they mean. And sometime towards the later part of the quarter, I will explain to you very clearly. There was a programming language called APL, array programming style, that at some point there was this thing going on among APL programmers that they could, the language was so expressive that it could express, you know, very complex things in just one line. In one line of code, you could do the most amazing things, but it's incomprehensible. You look at those symbols, you know, the language has all sorts of crazy symbols. You look at it like, what is going on? It looks completely foreign, like, you know, like extraterrestrial graffiti. So shortness and conciseness is not necessarily the goal. Okay, even though some cultures out there in programmers think that it's kind of cool that you were able to shorten by, you know, you were able to do it in a line or whatever, if somebody had done it before in 10 lines. But, you know, if you can't really understand, then that's no point in making it short, okay? However, making it short and better, that is a good thing. In fact, even for writing papers, right, and writing books, so, you know, there's that saying that I made it long because I didn't have time to make a shorter version, right? And that's true. Sometimes it takes longer to make shorter versions that are really good and more concise and more meaningful. And so, as I said, so conciseness by itself is definitely not a goal, but being concise and being expressive is the right combination. You should always strive for that, right? And how do you do that? So what's the key to doing that? In this particular case, it is a good example, okay? What is going on in here is that it's using abstractions that somebody else already wrote, right? All of these libraries, regular expression, the collections library, these are all things, or you know, the powerful split function, right? These are all things that are already in Python, in the Python ecosystem. It was written by somebody else. So it has meaningful names, okay, that we know what it means. So if we can use abstractions that already exist, that's the way to go. Absolutely. In fact, you could do this in one line of code if somebody else had already done a, you know, term frequency function, right? Term frequency, and then the path of a file. That's it, one line. Okay, that was the shortest possible program. So how to get to things that are short and expressive? Use libraries, right? That's sort of a lesson that is somewhat not very widely used in the C ecosystem. So C and C++ are notoriously bad at libraries. There's just, people need to write things by themselves over and over again. You know, programming means that you have to do everything. Even some of these basic abstractions, you kind of have to do it yourself. Other languages, for example, Python is an excellent example. They are booming with libraries. There's libraries for just about everything. Anything that you might think, there's probably a library that already does it for you. Is that true? Am I saying true for those of you who know Python?
Yeah, that's quite true.
Yeah, it's really amazing. And so languages these days are characterized not just because of the language and the syntax and whatever, the style or whatever that language, but the ecosystem around it, the libraries that already exist that really, really help, right? That's one of the reasons why people flock to Python is because of these libraries. It's just amazing, right? And so that's right. Python is all about calling libraries, that's for sure. It's really amazing. It's really amazing what the community around Python has done. I think they did that better than anybody, any other language. So yeah, basically, if you can use the work that somebody else already did that does what you want and it has a good interface and a good name, that's the way to go. Don't reinvent the wheel, don't write it from scratch. That's definitely the way to go.
I mean, it's not necessarily only about expressiveness. It also ensures that you do not introduce a new buggy code, because
right.
all of that debugging has already been done by someone else.
Exactly, absolutely. I mean, using third-party libraries, usually there's a team for that library or somebody that has dedicated time of their life to testing things and making sure that it works really well. So yeah, that's in terms of quality and assurances, that's another reason for using somebody else's code. So I mean, for using things that are already out there. Yes, so there's short and there's short. That's my point in here. That shortness is in itself is not a goal, but short conciseness and expressiveness, and you do that by basically calling abstractions that already have existed that somebody else wrote. That's the way to go. Which is, I mean, the most striking thing is the difference is really enormous between people who are most versed in C or C++ and people who are most versed in Python, things like that. It's a completely different mindset, right? Because the people who are trained in thinking in terms of C and kind of that monolithic style, their first reaction whenever they're given a problem is to write everything themselves, right? And people who are used to the Python kind of mode of development, the first reaction when given a problem is to search up what's the library that already does it for me. It's two completely different approaches. And definitely, reusing libraries is a very good thing from the point of view of software engineering. Now, with respect to size, that was another thing that I wanted to talk about. So in the Code Golf chapter, I discussed a little bit about software metrics and lines of code and things like that. And believe it or not, there are still companies out there that measure programmer productivity in terms of lines of code, which is crazy. But yes, so there's for a long time, lines of code has been a measure of programming productivity, and meaning that the more lines you wrote, the more productive you were, which is crazy in the world of Python, for example. But so there's all sorts of things that kind of spun up during the 70s and 80s in terms of software metrics. In terms of trying to measure the complexity of code, like, so for example, how can you describe, besides what I just said in terms of using abstractions, how can you describe something like this? Okay, so this code Golf, this short program, how can you quantitatively say that this is better than the monolithic style? Okay. So that's a concern that certain managers had. Like, you want to encourage programmers to develop in a certain way. How do you quantitatively say that this is better than the monolithic style? So there's a bunch. This is where we come to software metrics. So lines of code is one of them, but another one is cyclomatic complexity. It's one of the famous software metrics. that try to measure the complexity of the logic itself, complexity of the code in terms of control flow. So it measures how many for loops do you have, or nested for loops, how many nested conditionals you have. So there's a sort of a way of counting the cyclomatic complexity of a code. Clearly, this one would be very low. The cyclomatic complexity of this particular code here is very low. And the cyclomatic complexity of the other one, of the monolithic style, will be much higher. Where is it? This one. This one will be much higher because the way that you calculate the cyclomatic complexity, it takes into account nesting of control. So, this one's pretty bad. It goes into, 2 for loops followed by a conditional, followed by another conditional, and another one, and another for loop. And this is very nested. So this is going to have a very high cyclomatic complexity. So there's a whole part of software engineering that has to do with management in a way, and trying to explain, quantitatively why this is bad, right? Why is this bad, and why is the other one better? Well, cyclomatic complexity might be a quantifiable way of saying that. But again, cyclomatic complexity also has, all software metrics also have their problems. Okay, so these are the 4 very basic styles that gravitate around the notion of some sort of an abstraction, or the lack of it. We start with a monolithic style that has no abstractions at all. But then once you have this concept of abstraction and divide the problem into sub-problems, how do you chain them together? That's where the rest of the course goes. How do you chain these things together? And so we've seen a few of them here. The cookbook has the idea that the data sits somewhere, and the purpose of these abstractions is to make transformations on that data, destructive transformations on that data. That is the procedural style. The very basic functional programming style is that there's no data anywhere. There's just input and output, and you chain the functions together as in mathematical functions. That's the idea, mathematical function composition. And then we have the other one, the code goals, the conciseness in terms of trying to be very high level by means of using abstractions, that very powerful abstractions that somebody else already wrote for us. So all we need to do is know what those abstractions are, where to find them, and then call them and understand the API, basically understand their API, understand how they are used, what they mean, the concepts in there, and then use them, just use them rather than reinventing them, coding them ourselves. So that's definitely a sort of another way of thinking about writing from scratch versus using somebody else's abstractions, right? So when we're talking about abstractions, we may be talking about our abstractions, that we divide our problem into our own things, but we can also be talking about somebody else's abstractions. And in that case, we don't care necessarily about how those abstractions are implemented. We just care about what they mean. How are we going to use them, right? So that's basically the basics of programming. The 4 things, monolithic, no abstractions, abstractions that are kind of chained through the data, abstractions that are chained through function composition, and abstractions that somebody else wrote, and we just use them. Okay, so those are the 4 stepping stones of programming, and the opening salvo of the rest of the course.